Hi everybody, we are back with Unit 2, Day 4. This is Linear Measure Part 2. So first of all, let's get a little bit of algebra review because we're going to be using this in our work today. So when we're solving an equation, we want to solve for x. Remember that the idea is that we're trying to isolate our variable here. And in doing so, we can kind of organize our work with a line through the equal sign. We're trying to isolate that variable, and so everything that's surrounding the variable needs to be cleared to the other side. So right now we're seeing a minus 12, which if we were to perform the inverse operation, that's adding 12. So I'm going to start by adding 12 to both sides so that I undo my minus 12. This lets me bring down my 3x, my equals, and then if I go ahead and add my 41 and my 12, I will get 53. So now I want to get, I'm still trying to get x alone, right? And the 3 in the front is through multiplication. So if I undo that by division, so this is going to cancel on the left, leaving me with an x. I could leave this as a fraction, 53 over 3. Or if I wanted to approximate it, I could actually divide it out. But that's the idea of trying to isolate my variable and get it all by itself. Let's look at B. This one's a little bit different. Still, the goal is to isolate my variable, which is m. But notice that this time I have two terms with m's, and they're both on the same side. So if I go ahead and combine those like terms, I will get a 5m. I want to go ahead and bring down my plus 6 and my equal sign and my 16 because I haven't made any changes there, right? And I'm still trying to get this m by itself. So using all of my inverse operations, the opposite of plus 6 would be to subtract. So I'm first subtracting 6 from both sides. This lets me bring down my 5m, my equal sign, and my 10. And again, I'm trying to get m by itself. So the opposite of multiplying by 5 would be division. So I'm going to go ahead and divide both sides by 5. And this will leave me with an m equals 2. And this would be my answer. Just a little bit of algebra review. Last one is a scenario where I have a variable on two sides of the equation. And the goal here is still going to be to get my y's, or I'll say my y needs to be isolated, but I need to collect my y's for that to happen. So because they're on two different sides, let's go ahead and work to collect them onto one side. So right now, if I want to undo the minus 3y, I can do that by adding it to both sides. Notice that I'm adding it only to like terms. So I'm going to have everything cancel on the left, leaving me with a 15. On the right, this becomes a 7y minus 6. And again, because I'm trying to get y by itself, this is the variable I'm trying to isolate, then I need to use my inverse operations. So add 6 to both sides. This is going to give me a 21 equals 7y. And right now, this is 7 times y, which I can undo through division. So I'm going to divide both sides by 7. And this will leave me with 3 equals y. And that would be my conclusion here, is that y equals 3. So a little bit of mixed review with algebra, just to set the stage for what we're doing with our geometry today. So we want to write the segment addition postulate from yesterday for each example, and then find the value of the variable, or the segment measures. Okay, so here we have the full measure, AC, is defined as 59. AB is 11. And BC is defined as 4x. So if I were to write my segment addition postulate, I'm saying, first of all, that AB plus BC equals my full line segment AC. Right, so that's just the segment addition postulate. And now I'm going to substitute out each of these little segments here with their appropriate measure. So if we know that AB is 11 and BC is 4x, and AC is 59, here I have substituted each of my line segments with their appropriate measure, and I've now constructed an equation to solve. And so just like we did up above, where I'm trying to isolate my variable, right, I want to get x by itself here. So I need to employ all of my inverse operations, which in this case would be subtracting 11 from both sides so that they cancel. Bring down my 4x. This will equal 48. I now want to divide both sides by 4 because that undoes the multiplication. And I'll find that x equals 12. So that was the measure of just my variable. But notice that I also wanted to find the measure of the full line segment BC. And if I know that BC was equal to 4x, x is 12, then I can substitute my 12 in for my x to find that BC would be the product of 4 and 12, which is 48. So that is the measure, the full measure of the line segment. This should be A. This is D. That's all right, it's a letter. Differentiating it from a number. Okay, so here we have our second scenario. So I have a partial segment, WV is 2y plus 11. My other partial segment, VU, is y, and the full segment is 44. So if I write just my geometry theorem here, which is that, or postulate, WV plus VU equals the full length WU, right? So I'm just creating my structure for how these line segments relate. And now I can go ahead and substitute those values in. So WV, we know, is 2y plus 11. VU, we're told, is y. And WU, we know, is 44. So here I have set up an equation to solve for my variable. Notice that there's nothing in front of my parentheses, so I actually didn't even need to write the parentheses. I'm also seeing that I have two terms with y's. So let's go ahead and drop our parentheses first. 2y plus 11 plus y equals 44. And I'm seeing that I want to combine my y's, 2y and 1y, together making 3y plus 11 equals 44. And once again, I've created an equation to solve. I want to isolate my variable. So using my inverse operations, let's subtract 11 from both sides. That's going to allow me to bring down my 3y, and this will equal 33. Right now I have 3 times y, so to undo the multiplication, I'm going to divide. So if I divide both sides, I get y equals 11. So that's just my variable. So I know that line segment VU is equal to 11. But over here, WV is equal to the whole expression 2y plus 11. So if I know that y itself is 11, then the full expression I will need to substitute an 11 in for my variable, and I'll find that I have 22 plus 11, which is 33. So that's where I can find a variable, but also find the full segment, the full line segment. Okay, let's check out another example. So now we have several questions about one line segment in particular. So we're told that MO is 32. So the full length MO is 32. And we want to find the value of each of the following. So let's first write our segment postulate. So we know that MN plus NO equals the full length MO. And if I substitute in my known values, MN is 3x, NO is x plus 16. So here I have 3x plus x plus 16 equals the full length MO, which we know to be 32. Right? And now I can start solving. I can combine my like terms as 4x plus 16 equals 32. And now I'm going to kind of get a little faster with this. I want to subtract 16 from both sides, so I would have 4x equals 16. Then divide both sides by 4 to get x equals 4. So returning to my first question, x is just 4. Mn, we know, is the expression 3x, but because I know that x is 4, I have 3 times 4, which is actually 12. And then I can do the same thing with NO. We know NO is the expression and x plus 16. In this case, my x is 4, so I have 4 plus 16, which gives me 20. So it's a lot of substitution, kind of bouncing back and forth between the algebra and the geometry here. And in this next scenario, we again have a full measure, AB. Well, this is not the full, this is a partial measure, 15. And we know the full length, AC, is 5y, and then the other partial length, BC, is 2y. So if I first write my postulate arrangement here, I know that AB plus BC equals the full length AC. And here I go substituting in. I know that AB is 15, BC is 2y, so 15 plus 2y equals the full length AC, which we know to be 5y. And remember, I'm trying to solve for my variable. So I should notice here I need those variables together on the same side. So if I go and subtract 2y from both sides of my equation, I'm left with 15 equals 3y, which if I divide both sides by 3, I find that y is equal to 5. So this is just the variable alone. If we know that AC is the full expression 5y, then I use my information that y is equal to 5, so I know this has to be 5 times 5, which is 25. BC, we are told, is 2y. That's just based on our diagram. And again, we found y to be 5, so BC is actually just 2 times 5, which is 10. So once again, we can use the algebra to update our understanding of the geometry. Okay, the next one has us, assuming that J is between H and K. So we're going to have to draw something here. So if I draw a line segment and I'm supposing that J is between H and K, and they're telling us to find the length of each segment. HJ is 2x plus 4. So here I have 2x plus 4. JK is 3x plus 3. And the full KH, this whole thing here, is 22. So once again, I have all the information that I need to build an equation, right? If I know my line segment, HJ plus JK equals HK, and I'm going to be substituting my information in. So HJ is 2x plus 4. JK is 3x plus 3. And HK I can substitute out as 22. So now I want to go through and combine like terms. So I have 2x with 3x, altogether being 5x. 4 and 3 combining to make 7. We know this is equal to 22. If I subtract 7 from both sides, I get 5x equals 15. Dividing both sides by 5, I get x equals 3. So I know x is 3, but I wanted to actually find the line segments themselves. So if x is 3, if I jump back in here, then for my HJ, I have 2 times 3 plus 4, which is 10, because that's 6 plus 4. Over here, 3 times 3 plus 3, that's 9 and 3, which is 12. So I have found that HJ is 10, JK is 12, and then of course KH was given to us. Okay, F is the same thing. We want to again build a diagram and solve. I'm going to kind of pick up the pace here a little bit since the hopefully by now you're getting a little more fluid with the algebra. So if I know that M is between L and N, ML is 6x plus 20, MN is 150 minus 20x. The full length LN is 100. And we want to find the length of each. So once again, we know that these segments have to add. So 6 plus 20 plus 150 minus 20x all equals 100. If I combine like terms, my 6 and my negative 20 make a negative 14x. My 20 and 150 make a 170. This is all equal to 100. And now I'm solving for x. So I'm going to let this kind of run over. I'm going to subtract 170 from both sides. So I have negative 14x equals negative 70. Divide both sides by negative 14. So if I divide both sides by negative 14, I would get x equals 5 because dividing a negative by a negative gives me a positive. So there I have 5 as my variable, but remember I have to pop these back in. So I have over here 6 times 5 plus 20, which would be 30 and 20 or 50. Over here I have 150 minus 20 times 5. That ends up being 150 minus 100, which is, wow, 150 minus 100 is 50. There we go. So we have our line segment LM equal to 50, and MN is equal to 50. And notice that 50 and 50 add to 100, so that checks our work. Okay, now let's look at using kind of some different notation here. Now they're telling us, they're saying it's given that ST is congruent to SR. So ST, if it's congruent to SR, these two lengths are the same. And then it's also telling us that QR is congruent to SR. So once again, all three of these are the same measure. If they're all the same measure, then they're congruent, so they're equal. So I can take these expressions, which are given to me, 16 minus 2x and x plus 2, and equate them. So 16 minus 2x equals x plus 2. And now I'm just solving for x. So with my algebra, I could add 2x to both sides, which would give me 16 equals 3x plus 2. I could then subtract 2 from both sides to get 14 equals 3x. And then I finally want to divide both sides by 3. So we won't always have a nice, clean whole number. Sometimes it is a fraction. It is always frustrating when it works out that way. But our answer here, we would say that 14 thirds is my x. So sometimes you will have fractions for answers. Okay, and the next one here, again, congruent statement is telling me that xy is congruent to yz, and then wx is congruent to xy. So once again, all three of these are the same measure. And this time it's asking for me to find xy. If all three are the same, then this measure has to be equal to this measure. So I'm going to go ahead and say that 6x equals 4x plus 5. And let's solve for x. So if I subtract 4x from both sides, I would get 2x equals 5. Divide both sides by 2, I would have x equals 2.5. But notice it's not asking for x, it's asking for xy. So if I were to take 2.5 and plug it back into either spot for x, I would get the same measure. So let's just go and see with 6 times 2.5. If I go ahead and multiply these together, I would get 15. And over here, 4 times 2.5 plus 5. If I take 4 times 2.5, that's 10, plus 5 is also 15. So either way, I get 15, and so I know that xy is equal to 15. The measure of line segment xy is 15. Last problem here is breaking it up a little bit more even and telling us that AE is equal to 40. So this full length is 40. AB, so this guy is congruent to BC. So these two are the same measure. BC is 8. If I know that BC is 8 and AB is congruent, then AB also has to be 8. Right? And then it's telling me that CD, let's change our color here. CD is congruent to DE. And so we're looking to find what is true based on this information here. First of all, before we even look through our options, let's find what these missing lengths are, CD and DE, just to make our life easier. So if we know that we've already used up 16 of the 40, that leaves 24 left for this upper segment, right? So this is 24 left. If there's 24 left and these two measures have to be the same, then half of that 24 has to go to each green segment. So this is a 12 and a 12. So let's just see if that information helps us in our options. So if it's asking us, is AC equal to CD? So is AC equal to CD? No, because 16 is not equal to 12. How about is AB equal to BC plus BC? So AB is 8. BC we found to be 8 as well, so no, that's not true either. How about is BD equal to BC plus CD? Yes, according to our segment addition postulate, those are BC and CD are the two components that make up BD. So yes, we would keep that one. And then they're saying, well, is CE, this full length here, I feel like we have too many colors going on, is from C to E, is that twice the measure of C to D? Yes, because C to E is 24. That is double 12. So this is also correct. And then finally, we're looking to see, is AE, the full length, equal to the sum of A to C? I feel like we needed, let's change the color even again. Is that the sum of A to C plus C to D plus D to E? Yes, that covers the whole way. So those would be our answers there. And that wraps up our notes for